Hi, my name is Henning, and in this video we will talk about the economy of 3D print. We will initially go through traditional cost calculation, then we will look at the business case evaluation, and finally we will give an example of what we have been through. First we look at traditional cost calculation. When you have to choose between different manufacturing methods, you often make a cost calculation to judge between the alternatives you have. Here we show an example of a comparison where we, on the top, have the calculation for traditional manufacturing with all the cost contributions. And at the bottom we similarly have a calculation for additive manufacturing where the cost elements are highlighted with green. Here we see a typical picture of traditional manufacturing versus additive manufacturing. The dotted line shows traditional manufacturing where you have high initial costs, while for the additive manufacturing you have lower initial costs and approximately the same cost per part no matter how many you produce. For the traditional manufacturing you have to depreciate the high initial cost over the number you produce. And then at a number of X you have break even, meaning that with a number lower than X, you would probably choose additive manufacturing, while for a number higher than X, you would choose traditional manufacturing. However, this method only gives you a limited picture of the situation when you consider to use additive manufacturing. Conventional cost calculation and comparison of 3D printing and traditional manufacturing shows only a limited picture and often not in favor of 3D printing. Why is it then that people choose to produce using additive manufacturing? To set up a correct business case, you need to look at more than just the costs and savings. And that is what we are going to look at here. So in addition to costs and savings, you need to take into account the added value. To be a bit more specific, we here show some examples of what the cost contributions may be and what the added value elements may be. To the left you see the cost contributions, the well-known ones from normal calculations, and to the right examples of added value. It may be new features for functions, it may be a shorter delivery time, shorter time to market. It may be individual adaptation of a part to human beings, or you may open up new markets, for instance, or your maintenance cost may be reduced because you have 3D printed a part. But the essence is how much is it worth to put money on each contribution. This graph shows a way of illustrating the different contributions for added value. As you see, the arrows point both upwards and downwards. The upward pointing arrows indicate a positive effect, and the downward pointing arrows indicate a negative or an extra cost by introducing a 3D print. At the end you have to sum up all contributions. If the sum arrow points upwards, it is a positive effect by introducing 3D print, and it may indicate that that's the way to go. While if it points downwards, a sum arrow that shows an extra cost, it's probably not a good idea to go to additive manufacturing. On this slide, we specify some situations where 3D print may add value. Not always, but it may. As number one, if you have designed a part in such a way that it's the only option to produce using 3D print, that's obvious. Then if traditional fabrication is expensive or with high complexity, it may also be worth considering 3D print. The batch size is limited. We are not talking millions of parts. We are talking tens, hundreds or thousands or even tens of thousands of parts with the present level of 3D print technology. If you by traditional fabrication have large material waste, it may be worth considering 3D print. If it makes sense to consolidate parts, integrate them into one piece, it may make sense. If you are able to reduce your operating cost, by smart design that is 3D printed, it makes sense. If you have frequent design changes and want to go to the market but are not sure you have finished your design, it may make sense to start with additive manufacturing. If you have high storage costs and can produce on demand, it may make sense. If you have long delivery time and the breakdown of your equipment is expensive, you can make a quick fix using 3D print. You can customize parts knowing that producing one part costs you approximately the same as producing several parts per part, and you can personalize, adapt things to individuals using 3D print. Finally, we have an example where we illustrate what we have just been through. The example shows a flight buckle for a safety belt. To the left you have a traditional buckle, and to the right you have a buckle optimized for additive manufacturing. The challenge is to reduce the carbon footprint by using 3D print. And how is that done? The solution is to optimize the design for 3D print and print it in titanium alloy. What was gained by that? Well, the result was a weight reduction of 55% from 155 grams to 70 grams. That's not much, you can say, but for an Airbus 380 with 853 seats, it sums up to a total weight reduction of 73.5 kilo. And it has been calculated that over an airplane's lifetime, each kilo contributes to a fuel consumption of 45,000 liters. For the 853 seats, that means then that the 73.5 kilo weight reduction reduced the fuel consumption with 3.3 million liters, corresponding to a saving of 2 million pounds over the airplane's lifetime. In addition to that, you have improved strength and you have simpler scrapping or recycling at the end. So we go from several materials to just one. So that's a simpler recycling. A way to illustrate this is to make a list of where you have impact by changing to additive manufacturing. And the arrows illustrate the positive and negative impact you have, where the green upward pointing arrows show a positive effect and the negative effect is illustrated by downward pointing black arrows. And the overall positive effect is shown by the big green arrow for the operating cost, meaning the fuel savings. A way to illustrate this is the graph to the right, where you have the different contributions, downward pointing and upward pointing arrows, summing up to a big positive effect to the right, indicating the big fuel save by this change to additive manufacturing. Putting figures on this, at the top we have the fabrication costs, and the conventional buckle sums up to about 10,000 British pounds for the full aircraft. Using additive manufacturing, we first have to invest in the R&D work, which is quite costly, namely almost 1.5 million British pounds. And on top of that, the fabrication cost or manufacturing cost for the titanium buckle is 165,000 British pounds, meaning almost 17 times higher than the traditional buckle. And together we get an extra cost for the first plane for 1.6 million British pounds. Why is it then that it makes sense to go to additive manufacturing? That we see at the bottom for the added value, because you have the big fuel saving of 2 million British pounds per plane. That gives us a saving for the first aircraft of almost 400,000 British pounds, while for the following aircraft you have a saving for each of them of 1,845,000 British pounds. On top of that, you have some benefits that are more difficult to quantify economically. Namely, you have an improved strength of the buckle, and it's easier to scrap and recycle. So, summing up at the bottom, the total impact for the first aircraft is the benefits and a sum of almost 400,000 British pounds, while for each of the following flights you have the benefits plus 1,845,000 British pounds by changing to additive manufacturing.